In this short example problem, we're going to look at a point load flexure test that was conducted by a friend of mine while I was at the University of Texas, Austin. So here is the test. You can see in the test the progression of flexure cracks up the beam. And then eventually these cracks curve in and you can see the failure of the compression block in the top. Feel free to rewatch this video a few times as needed. This 2-point load test with on this kind of piece of a wall slab. So that's kind of why it has this weird geometry. We give the measured material properties, and then we can look below. And as I said, what I want us to find is the nominal capacity of the section, the first cracking load, the load deflection, and the load deflection relationship. So we're starting into the nominal capacity of the section. So this should be pretty familiar by now. But we'll start with tension equal to compression because we don't have any applied external load. So our tension, we're assuming that our steel yields for both tension and compression. And then we have our concrete compressive component, 0.85 F prime C, B, beta 1 C. So let's just mark our assumptions. So we're assuming yield here. We're assuming yield here. So we can solve for C, and we'll find our C equals AS Fy minus AS prime Fy over 0.85 F prime C beta 1 times B. So you can see, I mean, we don't need to go any further. You can see in the top that Fs prime can equal Fy. If it did, then our C would equal 0, and our compression block would be 0. We wouldn't have any concrete component. So we'll just switch that right here, and we'll say AS Fy minus AS prime Fs prime over 0.85 F prime C beta 1B. And I mean, I guess I can note this because we have an equal amount of compression and tension steel. So then if I plug in some values here, we had 3 number 11 bars times 69 KSI minus 3 number 11 bars times Fs prime. And this is all over 0.85 times 4.2 times 0.84, which is our beta, times 36 inches, which is our width. So using strain compatibility, we can find that our Fs prime is equal to ES, our modulus of the steel, times C minus D prime over C times 0.003. So then we can find our depth of our compression steel. So our D prime is equal to 3 inches plus 1/2 of the diameter of our number 11 bars. And this will be about 3.7 inches. So then we can use this and solve for C. So we'll use the above expressions, and we can find our C to be 1.59. You can either do an iterative procedure to find, I guess at what points these two equations above will equilibrate, or you can plug in your fs prime above and just solve for C using a quadratic. So we'll find then that our fs prime is equal to negative 0.02 ksi. So you can notice that our compression steel is really in tension in this scenario. So we can calculate our curvature then as well, which we'll need then. So EC over C, or epsilon C over C, so our strain at the ultimate over 1.59 inches equals 18.9 times 10 to the negative fourth radians per inch. And then we can also calculate our moment capacity. And our moment capacity is AS Fy d minus beta 1c over 2 plus AS prime Fs prime times d prime minus beta 1c over 2. So we can plug in our values and we'll find our nominal moment capacity of 6,660 kip inches. So this can be compared to the actual moment. So our applied moment for this specimen, we found that the point load P was our P test was 125.5 kips. So then I guess using our geometry, we know our shear diagram. It's P up, P down, P down, P up. And our moment diagram then is just a slope up and constant slope down. And this is 56p. Because this is 56 inches. So then we can find our mu, and this was just 56 times 125.5, which will be around 7,000. So you can see that our calculated capacity is pretty close to our actual capacity, and it's conservative, which is good. All right, and I guess we didn't include self weight, so it's actually going to be a little closer than what we actually got. Okay, so next we can find our first cracking load. So to find our first cracking load, we'll need to find our, I guess, first our modular ratio, so we know how to transform our sections. So we're given EC. This was measured during the test. So then we can find our modular ratio, which is just ES over EC. And this will be 29,000 KSI over 3,840 KSI, which will give us a modular ratio of 7.6. So now we'll need our uncracked transformed section. So to find our uncracked transformed section, we'll first draw our section so that we can know what we're working with. We have steel on the top and steel on the bottom. The top steel at distance d prime from the topmost fiber, and the bottom steel at distance d. And we know we have AS prime times n minus 1 and AS times n minus 1. So the depth of our top steel D we can find as 24 inches minus 2 inches minus 1/2 times the diameter of our number 11 bars. And this will be 21.3 inches. So now we're ready to find the rest of our properties. So first we'll find our area of the steel. So AS equal to AS prime is 3 times 1.56, and this will be 4.68 square inches. And then the centroid of our section, then we can find just taking the distance to each of the centroids of our areas. So first, looking at times the area. So first we'll have the concrete area, so 24 inches times 36 inches times 24 inches over 2. Next we can do one of the steel areas. So we'll have the first, the lower steel, so we'll transform it, so 7.6 minus 1 times our AS, 4.68, times 21.3 inches, and then adding in our compression steel, 7.6 minus 1 times 4.68 times 3.7 inches, which we found above. And we take all this divided by just our areas. So 24 times 36 plus 7.6 minus 1 times 4.68 plus 7.6 minus 1 times 4.68. And we'll find our y to be equal to 12.3 inches. So next we can find our uncracked moment. So our I uncracked transformed. So I guess, yeah, our I uncracked transformed then is going to be the summation of all of our BH cubed over 12s plus area times d squared. So this is parallel axis theorem. Alright, so we'll start with our concrete area. So our concrete area, or sorry, our concrete moment of inertia. So concrete 36B times 24 inches to the third over 12. Plus now we need our AD component. So A times our d, which is 24 inches over 2 minus 12.3 squared. Alright, so next we need to add our first steel layer. So 4.68, and we need to transform it. So we'll have 7.6 minus 1 times 4.68 times 21.3 minus 12.3 squared. And then we'll add our last steel layer, our compression steel. So 7.6 minus 1 times 4.68 times 3.7 minus 12.3 squared. So doing the math here, we'll find that our uncracked transformed is around 44,000 inches to the fourth. So to find our cracking moment, we'll need to find the concrete tensile strength. So our FT is just 7.5 roots of our concrete strength, which was 4,200 psi. And if we do the numbers here, we'll get 490 psi, or 0.49 ksi. So we can use this to find our M cracking. So our M cracking is going to be our FT times our uncracked transformed moment of inertia, over C. So this will be 490 psi times 44,000 inches to the fourth over 24 inches minus 12.3 inches. So this is the distance from the centroid to the bottom fiber. And this will give us a cracking moment of 1,832 kip inches. And yeah, let's change this to be consistent with our units. Okay, so next we can calculate the curvature before cracking. So we'll have our strain diagram that we've been working a lot with. We'll have our curvature there. And we know this distance. Okay, so what we can do is we can find our phi before cracking. And our phi before cracking is going to equal our strain at cracking over the distance from the centroid to the bottom. So we can plug in our values, and the strain at cracking is going to be our cracking stress, so 0.49 ksi, divided by our concrete modulus, 3,840 KSI divided by 24 inches minus 12.3 inches. And this will give us a curvature before cracking of 1.08 times 10 to the negative fifth radians per inch. Alright, so next we want to find our load deflection relationship, and we have a couple points for it so far. Alright, so 7.1.3. So we found our, we were looking for our first cracking load and our first cracking curvature, or our before cracking curvature. Alright, so now we want our load deflection relationship. Okay, so for this we're going to need to calculate our yield curvature. And in order to calculate our yield curvature, we need to calculate first our crack transform moment of inertia. So I'm going to draw our crack transform section. So we have our concrete, we have our compression steel, assuming that it falls in the top block, and then we have our tension steel. So our tension steel, we have AS times N. Our compression steel, we have AS prime N minus 1. And then our area here, we have a height of KD and a width of B. Distances down, we have a distance D prime, and then a distance down to the bottom of D, which we calculated before. Alright, so first we need to find our neutral axis depth. So our neutral axis depth is going to be our area of concrete, B, times KD, times KD over 2, the distance to the neutral axis from the centroid of that section. And then we have AS prime, N minus 1, KD minus D prime equals D minus KD times N times AS. So simplifying this, we can get to the point of having a quadratic. So we'll have B over 2 times KD squared plus N AS plus N minus 1 AS prime times KD minus D times N times AS minus D prime times N minus 1 times AS prime. And this will equal 0. So if we plug in our values, we'll get our quadratic of 18 KD squared plus 66 KD minus 866.3 equals 0. And then using the quadratic formula, we can find our KD equal to 5.34 inches. So now we can calculate our section properties. And just like before, our cracked transformed section. So I cracked transformed is just going to equal the moment of inertia of each of the elements plus the area times the distance squared. So we'll use parallel axis theorem again. So we can find B kd to the third over 12 plus B times kd times kd over 2 squared. So this is our concrete, plus, so this is our concrete component, plus N AS D minus KD squared plus N minus 1 AS prime KD minus D prime squared. So this is tension steel. And this is top steel or compression steel. Okay, and if we plug in our values here, we'll get our iCrack transformed to be 10,900 inches to the fourth. Alright, so we know our cracking moment from before. We know so we know our KD is going to be the same, and this is going to help us solve for our yield curvature and our yield moment. So we know the strain of the steel at yield. So our epsilon y is going to equal our Fy over Es. So it'll be our 69 KSI over 29,000. And this will be 0.00238. Will be our yield strain. So our yield curvature will then be just our yield strain over D minus KD. So this will be our yield strain over D minus KD, which was 5.34. So this will give us 14.9 times 10 to the negative fifth radians per inch. So we can then find our yield moment, which will just be E I times our curvature. And we can find this to be 6,250 kip inches. Alright, so now we're ready to estimate our deflections at first yield. Alright, so to do this, we can use whatever method we want. I'm going to find or use moment area, and for that we're going to look at our curvature diagram. So on our curvature diagram, it's going to mirror our moment diagram, where we'll have our yield curvature, well, 0. This is curvature. So we'll have an area of this triangle is going to be 1/2 phi times 56 inches, and our centroid is going to be 2/3 times our 56 inches. Okay, so our deflections we can find then, and our deflections, delta y1 is going to equal 1/2 phi y times 56 inches times 2/3 times 56 inches plus our phi y times 72 inches times the distance here, which will be 56 inches plus 36 inches. So this will give us a deflection of 1.14 inches. So and this is at first yield. So after this, we're just going to have an initial plastic rotation or plastic deformation. So the additional deflection will be a result of any additional plastic hinge capacity. Of the section. So our plastic hinge capacity theta p is going to equal our phi ultimate minus our phi yield times the length of the plastic hinge. So this will be phi ultimate minus phi yield times, we'll assume the plastic hinge length to be d over 2. And we know our phi ultimate from the first part of the problem, so we'll use just our nominal here, and we just found our yield curvature. We know our d, so this is going to be 18.5 times 10 to the negative third radians. Alright, so using this we can find our additional deflections. So for this we'll need to do a kinematic displacement diagram. Alright, so at first yield we'll assume there's yielding at both of the point loads. And what this is going to do is it's going to make our structure deform like this. So we can see that we'll have our plastic moment, our plastic rotation capacity here, and you can see our deflection after hinging. All right, so our additional deflection then. So our additional deflection is then delta y2, and this will be just our plastic rotation capacity times 56 inches. And we'll find this to be 1.04 inches. So we can then find our total deflections. And our total deflections then are just equal to our deflections at first yield plus all our additional deflections. And this is going to give us a total deflection of 2.18 inches. Alright, so we can use these points to construct our load deflection curve. So I'll let you guys do this on your own. But you can use our moment capacities to find our P's, and then we found our deflections. So this should be pretty straightforward. So you can see that using just our ACI nominal approach, we only got a total deflection capacity of 2.18 inches. So you can see, from our video that there was a substantially larger deflection than that. So if we were to use the Matic and Corley approach, we'll find that we can get larger displacements. To get closer to actual deformation. Okay, and that's the end of this